Okay, so let us start. Uh, so I hope you all joined by the new link, right? So now what we studied last time is about Cosy sequence. So this is how we define a Cosy sequence. We say that Xn is a Cosy sequence if and only if after a certain point, right? So after a certain milepost, any two components of the sequence are as close as we please, right? So the distance or length between or distance between xm and xn are less than epsilon is less than epsilon, right? For any m and m greater than n. Right? So this is how we define Cauchy sequence. And then we see an example of a Cauchy sequence. We see that 1 upon n is a Cauchy sequence. So today what we are going to do is we are going to see the results associated with the Cauchy sequence. First one is, write it as a lemma. Right, so the lemma, it says every Cauchy sequence is bounded, right? So you want to prove that every Cauchy sequence is bounded. If xn is Cauchy, then you know this definition is true, right? So that is obvious. So that is clear now that if xn is a Cauchy sequence, then for every epsilon positive, there exists n belongs to natural number such that xm minus xn is less than epsilon is the standard definition for the Cauchy sequence. So now we have to show that xn is bounded. So you want to show xn is less than absolute value of xn is less than some capital M for all n. That is what we want to show. So what we will do is we will first fix the epsilon, right? And so let epsilon be equal to 1 because epsilon can be any positive number, so you can fix epsilon as 1. If epsilon is 1, then you can rewrite this definition that there exists some n1 belongs to natural number such that xn minus xm is less than 1 for all m comma n greater than n. Right, so that is how we define Cauchy sequence, right? So xn minus xm is less than epsilon for all m comma n greater than n. So here epsilon is 1, right? So then what you have is this, right? So then right, so for all the m comma n greater than n1, right, because you fix n now as n1, so because of that you can say that because xn plus 1 is obviously larger than n plus 1 is n1 plus 1 is larger than n1, so that's clear for you. So now this is true, but this, by using a triangle inequality procedure, you know that this is less or equal to right. So this is because of triangle inequality, xn plus 1 absolute value of xn plus 1 minus absolute value of xm is less or equal to xn1 plus 1 minus xm. That is by triangle inequality. So if you combine these two, you get minus 1 less or equal to xn1 plus 1 minus xm less than 1. Right? So because you know this is less than 1, but this is less than absolute value of this. So when you remove the absolute value, you get -1 less or equal to absolute value of xn plus 1 minus xm is less than 1. Right? So what you can do is, right, so you can change this here and move this 1 here, right? So what you get is xm is less than or equal to xn plus 1 plus 1 4 whole m greater than n1, right? So xm is less than, right? So I can say strictly less than because this one is less than, so it's all less than, strictly less than, right? So here because you are strictly less than, all these are strictly less than, so this one is strictly less than. So what you have is for all m greater than n1, absolute value of xm is less than xn plus 1 plus 1, right? So absolute value of this. You know that. So what you want to show, xm is less than m for all m in natural number, not just these. So what you can do is you take capital M be the maximum among the numbers absolute value of x1, absolute value of x2, all the way up to absolute value of xn1 and this one, absolute value of xn1 plus 1 plus 1. Right? So you take m as the maximum among all these numbers, right? So once you take m as maximum of all these numbers, you can say that xn is less than m for all n belongs to natural number, because m is the maximum among these numbers. X1 is less than m, right? Or equal is fine. You can say equal also, right? Because maximum should be one of these numbers. So in that case, if x1 is the maximum, obviously x1 is less than m, x2 is less than m, x3 is less than m, xn1 is less than m. For any number larger than n1, all those xm's are less than xn plus 1 plus 1, right? So eventually all the xn is less than absolute value of xn is less than m for all n. So that guarantees that every Cosy sequence is bounded. And so we have proved that a Cosy sequence is bounded. Right? But now we can see that every Cauchy sequence is bounded. But now the question is, if a sequence is bounded, then can we say it is Cauchy? Right? So that is the question. Obviously, whether the converse of this results is true, right? If a sequence is bounded, then can we say it is Cauchy? So the answer is no. Not all bounded sequences are Cauchy. So we shall prove that result. So obviously, if you want to disprove the results, I told you several times that we obviously always give a counter example, right? So right? Bounded cannot imply Cauchy. So that is the converse of this result, and converse is not true. So you have to give an example. So you have to give an example which is bounded, a sequence which is bounded but not Cauchy. Right? So let me give you an example. So I call it counter example. Right? So if I take xn as minus 1 to the power n, right? So this is a sequence. Then clearly this is a bounded sequence, right? Because absolute value of xn is less or equal to 1, right? So xn is a bounded sequence, that is very clear. We studied this several times earlier as well. Now the question is if whether this sequence is Cauchy or not. That is what you have to show. Right? So you have to show this sequence cannot be Cauchy. Right? So to show that, again, we will use contradiction method. Right? So contradiction we studied earlier also. That is, you assume the opposite of what you want to show and then get a contradiction. Right? So if xn is Cauchy, right? If xn is Cauchy, right? Then there exists n belongs to natural number such that minus 1 to the power n minus 1 to the power m is less than half for all m comma n greater than n. Right? So you know for every epsilon positive, there exists a natural number such that xn minus xm is less than epsilon for all m comma n greater than n. Right? So in this case, we choose that. Right? So let's fix n. So that's easy. So I will name it as n1. Right? So you choose epsilon as half, right? And then you fix n as n1. So for some fixed n1 greater than this one is less than half. Right? So what we are going to do is we are going to show that this is a contradiction. Right? So absolute value of n, a minus 1 to the power n minus absolute value of minus 1 to the power m is less than half is what we have if it is Cauchy. So now we want to get a contradiction. So to get a contradiction, I have a fixed n1. So let me choose m and n as two numbers which are greater than n1. Right? So first thing I have to do is I have to choose m and n. So let me choose n is equal to 2n1 and m is equal to 2n1 plus 1. Right? So obviously both of them are greater than n1. Right? So that's clear. 2n is greater than n1 and 2n plus 1 is greater than n1. So that is clear here. Right? Okay. So in this case, right? So because these are greater than 2, oh sorry, n1, you can substitute here. So you know that minus 1 to the power 2 n1 minus 1 to the power 2 n1 plus 1 is less than half. Right? Because of the assumption you have that xn is Cauchy. But you know 2 and 1 is an even number. So minus 1 to the power 2 and 1 is plus 1. Okay, so this is equivalent to plus 1. Right? Minus 1 to the power 2 is 2 and 1 is plus 1. And minus 1 to the power 2 and 1 plus 1 is an odd number. So that is minus 1. Right? And then there is a minus here. So you get plus 1. Or I can say this is of minus 1 less than half. Right? So minus 1 to the power 2n is plus 1. And then this minus 1 to the power 2n plus 1 is minus 1. So that is minus 1. It's less than half. Okay, so what you have is minus 1 to the power 2n, 1 minus 1 to the power 2n plus 1, right? So that is minus 1 to the power 2n plus 2n 1 is plus 1, and then minus 1 to the power 2n plus 1 is minus 1. So when you combine this, what you get is this is absolute value of 2, that is 2 is less than half. And so what you have here is you have 2 less than half. So in that case, you can easily see that this cannot be true, right? 2 is less than 1 half cannot be true. So in that case, you know it is a contradiction. Right? So this is a contradiction. So if this is a contradiction, right, then you know xn cannot be Cauchy. Okay, so you can see that it is not Cauchy. Can you see the board now? Okay. So this is the way you show that something is not a Cauchy sequence, right? So this is called counter example, right? So, okay, thank you. So somebody earlier said the board is not clear, so that's why I am asking. So now you can see it. So this is here. I gave a counter example that xn is a bounded sequence, but it is not a Cauchy sequence. Right. So that is one of the properties of Cauchy sequence, right? So we see that every Cauchy sequence is bounded, but you cannot say the same for bounded sequence, right? Bounded sequence may not be Cauchy, right? So now, why we need Cauchy sequence? Right? That is an important question. So we use the Cauchy sequence to prove convergence of a real or sequence of real numbers, right? So we are going to show that if xn is a sequence of real numbers, then it will converge if and only if Cauchy, right? For sequence of real numbers, Cauchy and convergent are equivalent to each other, right? Cauchy implies convergence and convergence implies Cauchy. That is called Cauchy criterion. Okay, so this is called Cauchy criterion. I will write this as a theorem. Right, so Cauchy criterion. This is again an interesting property associated with the convergence and Cauchy sequence, right? But this is true only for real sequences, right? Not other sequences, but since you are in the first year and you are talking only about real sequences, you don't need to worry too much about what are the other sequences. But as long as the components of the sequence are real numbers, you can apply this criterion, right? Right, so we say that a sequence of real numbers is convergent if and only if it is Cauchy, right? So if the sequence is convergent, then you can show that it is Cauchy, and if the sequence is Cauchy, then you can show that it is convergent, right? So we have to prove two ways. So first, to prove this, let us go this way, right? Suppose, right, so suppose Xn is a convergent sequence. Right, so if Xn is a convergent sequence, then you know that it has a limit, right? So it has a limit. Okay. So if it is convergent, then you know it has a limit. So clearly you can say L is the limit, right? Without any worries, you can say L has the limit. And that is a standard notation we use. Okay, so then the definition comes. For every epsilon positive, there exists n belongs to natural number such that xn minus L is less than, let me say, epsilon over 2, right? Just for a purpose, I write it as epsilon over 2, or you can say epsilon as well, it doesn't matter. And for all n greater than n, right? So for all n greater than n, xn minus L is less than epsilon over 2. But if you want to show it is a Cauchy sequence, then you know you want to get xm minus xn or xn minus xm, right? So for all m and n greater than n. So let's take m and n. Now you take some m and some n greater than n. So in that case, as long as the index is greater than capital N, right? Xn minus L is less than epsilon over 2. At the same time, xm minus L is less than epsilon over 2, right? Because as long as m and xn are, so m and n are greater than capital N. So now you can easily see that the Cauchy condition, right? You want to show xn minus xm is less than epsilon, right? So this is what you want to show. So you can rewrite this as xn minus L plus L minus xm. Right? So you can write this as xn minus L plus L minus xm. So again you apply triangle inequality. The triangle inequality says this is less than xn minus L plus this is less than xm minus L. You can take a minus out and it become plus. And so this is triangle inequality. And this is less than epsilon over 2. This is less than epsilon over 2. So this is less than epsilon over 2 plus this one is also less than epsilon over 2. So now if you add both of them, you get epsilon. So this is why I put epsilon over 2 here, right? So if I put epsilon there, I will end up with 2 epsilon. So then you have to change everything at the end, right? So it is not a mistake, but you can always, if you know that earlier, you can always make it epsilon over 2 there, right? Suppose if I did not put this 2 here, right? I will have epsilon, 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 and then I will end up with epsilon 2 epsilon. So then at this moment I will realize, oh, I should have epsilon here. So I divide everything by 2, 2, 2 and come back and set things easy, right? So that's not a big issue, but what you have here is, so for all epsilon positive, you have their x is n belongs to natural number such that xn minus xm is less than epsilon for all m comma n greater than n. So that is the definition for Cosy sequence, right? So this implies xn is Cosy. Okay, so we easily proved that every Cosy sequence is, sorry, every convergent sequence is Cosy. And so that is an easy result, right? So now what we have to do is we have to prove that if the sequence is Cosy, then it is convergent, right? So we have to prove the converse of this result, right? So the converse of this result, to prove that we will use some of the results which we already have, right? So we prove that if the sequence is Cosy, then we say that it is bounded. So clearly you can use monotone convergence theorem and other related results, right? So boundedness is there. So that is one of the things we use for convergence earlier. So we shall do that, right? Okay, so conversely, so I'm going to prove the reverse now. Right, so conversely, I assume that xn is Cosy, right? But I already proved that Cosy sequence is bounded. Right, just at the beginning of this class, I proved that Cosy sequence is bounded. Right, so then if you assume xn is a Cosy sequence, then it is a bounded sequence. Bounded sequence, when it comes to bounded sequence, then one of the important theorems we studied in the last class or class before that maybe, right, which is called Bolsano-Weierstrass theorem, right? So we call Bolsano-Weierstrass theorem. That is a theorem which relates boundedness and subsequences, right? So let me write the results what Bolsano-Weierstrass theorem says. right? Bolsano-Weierstrass theorem, you have that the sequence xn, because it is bounded, right, it has a convergent subsequence, right? So we name the convergent subsequence as xnr, right? The standard notation which we have earlier, right? So if this is a convergent subsequence, then this will have a limit, right? So let's take limit r goes to infinity, xnr is L, right? So it is convergent subsequence only. So you take the limit for the index of the subsequence. So as r goes to infinity, xnr goes to L. That is how, that is what you can assume so far. Right? So now what we have to do is we have to show that limit of xn is equal to L. Right? So you want to show that, right? But we only have limit of the subsequence. So we will start by using that first, right? So definition, for every epsilon positive, there exists capital R, belongs to natural number, such that xnr minus L is less than epsilon. Again, I am using epsilon over 2 for small r greater than capital R, right? So this is how we define limit of a sequence. So in this case, it is a subsequence, right? So this is one result you have. At the same time, you have xm is Cosy. So you can write the definition for Cosy as well, right? Because it is assumed that xn is Cosy. Because xn is Cosy, right? You know that there exists n belongs to natural number. You know epsilon is here, so you can use the same epsilon, right? Such that xn minus xm, right? That is less than epsilon over 2 for n comma m greater than n. So you have two results. One associated with the Cauchy condition or Cauchy definition of Cauchy, and then the other one is with the Bolsano-Weierstrass theorem. Because of Cauchy, it is bounded, and because it is bounded, you can apply Bolsano-Weierstrass theorem, and then there is a convergent subsequence. Right. So what you have to do is to, now you have two numbers. One is R, and for some R greater than R, this result is true. And one is N, capital N, for some N, M and N greater than N, this result is true. Again, I may have to have this as epsilon over 2, right, to make it epsilon at the end. So now what I am going to do is I am going to take capital R1 or small r1 maybe. Right, so I'm going to take capital small r1 as the maximum among n and r, right? So if you choose n and r here and here, then you take the maximum among both of them. So in that case, right, right, so in that case, right, so here because your r1 is maximum of r, So this result is true for small r1, right? So then small r xn small r1 minus L is less than epsilon over 2. And this result is true for all m comma n greater than n, right? So for all m comma n greater than n you have, right? So then if you choose m as r1, right, then r1 is greater than n. So this result is also true for r1, right? So then xn minus, in place of m you take m as r1, right? So then xn r1, right, is less than epsilon over 2, right? So clearly you have these two results. Now you want to show xn minus L, right? So that is not a big deal now, because you want to get xn minus L. So that is clearly this, right? So xn minus xn r1 plus xn r1 minus L, right? You add and subtract an xn r1. So that is SO equal to, by triangle inequality, plus xn r1 minus L. This is less than epsilon over 2. This is less than epsilon over 2. So this is epsilon over 2 plus epsilon over 2, that is epsilon. So what you have is, for every epsilon positive, right? So here, for some n greater than n, right? So for every epsilon positive, there exists n belongs to natural number such that xn minus L is less than epsilon for all n greater than n. Right? So that is the definition for the limit. Right? So then clearly, right? So I can just write the final word here. Right? So for every epsilon positive, there exists natural number such that xn minus L is less than epsilon for all n greater than n. So limit n goes to infinity, xn is equal to L. So that is the definition for convergent. Right? So we say that the sequence is convergent if it has a limit. So we prove that the sequence has a limit. And so to prove the converse, we use several previously proved parts, right? One is Cosy sequence is bounded. If it is bounded, then by Bolsano-Weierstrass theorem, it has a convergent subsequence, and we take the limit of the convergent subsequence and then use the Cauchy condition, and Bolsano-Weierstrass result that limit of the subsequence and show that the sequence converges to the same limit. And that is how we prove the convergence of the result. In the next class, we are going to see an example of how you can show something is a Cauchy sequence and something is not a Cauchy sequence by using the convergence result, this theorem. And then we will see some other definitions of other types of limits, right? So that we will talk about in Monday class.